Today we are working on 6.2. It's quite similar to the one that we did last time. So here is the first problem. A radioactive substance has a half-life of 14 hours. A sample of, do you guys know what half-life is? 6.2, yes. So half-life is a measure of how fast something breaks down. So it's particularly used for radioactive isotopes, although you could do it with just about anything. So imagine you have some sandstone out on the desert, and as the wind blows and the rain comes and the rock gets smaller and smaller, you could say the half-life of the rock is 1,000,000 years, which means if you measure how much it weighs now and you come back 1,000,000 years later, it will weigh half as much. And then you come back 1,000,000 years later and it will weigh half as much. And will the rock ever totally be gone? Not really. You're just cutting it in half until it gets so small that you can't see it. Yes. So radioactive isotopes they're atoms that they're put together in such a way that they don't stick very well. Like gold, it's almost impossible to get gold to break apart. Like a gold atom stays gold all the time, right? It doesn't. And most atoms, you can't really change what they are. You can mix them with things and do chemical reactions, but an oxygen atom is always an oxygen atom. It doesn't become nitrogen or something else, right? We can blend it with different things, but radioactive isotopes are atoms, and they're usually quite large. Not all the time, but usually they're really big, and the protons and neutrons are held together in such a way that every once in a while the atom explodes. And when it explodes, it turns into two different atoms, and then pieces of it fly out, and we call those pieces radiation. And radiation is quite bad for us. Yes, that radiation can fly out and it can hit us, and it's like a miniature bomb going off, and those little atomic pieces are flying at us, and they can hit us and mess up our DNA, mess up our cells, and cause cancer and make us sick, do lots of things like that. Awesome. So, how fast do radioactive elements degrade? Well, we talk about them in terms of a half-life. So this particular isotope of uranium, so there are several different types of uranium out there, depending on how much it weighs, essentially. And this particular atom of uranium has a half-life of 14 hours, which means if you had 100 pounds of this stuff, 14 hours later, half of it will have exploded, will have fallen apart and sent radiation all over the place. So you have 50 pounds of it. You wait 14 more hours, and now you only have 25 pounds of it. So the formula for the half-life is this. So looking at that equation, find the initial amount in the sample and how much will be left after 30 hours. So right now, how much uranium do we have? Just looking at the equation. This right here. Okay? And after 14 hours, after 30 hours, we're going to plug that in there. And you have to make sure you use your parentheses correctly. So we do 2,400. The fractions need to be in parentheses. Like that. So 30 hours after we start, we go from 2,400 grams down to 543 grams. And that's a pretty quick half-life. Some radioactive things have half-lives in the millions. which means they break down really, really slowly. Some of them have half-lives in the seconds. No, you can't. It doesn't all. So a nuclear explosion is a little bit different because you are forcing the atoms to break apart by exploding them. Do you know how they work? You get a chunk of uranium here or plutonium, and you get a chunk here, and has to be enough of it. Have you ever tried to light a fire and you didn't have enough kindling and it fizzled out? That you have to have enough of the stuff, and then you basically put explosions on both sides, and you explode both pieces, and they fly together and hit, and when they hit, the whole thing just goes up at once. So, yeah, that's an atomic bomb. Yeah. Okay. Let's do. Do you guys want to see another one of these? Let's look and see if the next one's any different. Okay, so this one's not a half-life problem. So here is the value of a car. How much is the car worth right now? 18,500. Is the value of the car going up or down? Down how fast? What does 0.8 mean in an exponential situation? Going down. How do we know we're going down? It's less than 1. How far below 1 is it? 20%. So the value of the car is dropping 20%. So we take the 10 and we stick it in for t. Tyson's way good at this. You already finished, didn't you? Oh. Okay. Okay. Here we have an equation. This is bacteria dying in a petri dish. What is the initial population of the bacteria? 1,600. Is this a growth or a decay? Decay because less than 1. And how fast is it decaying? 15%. Because we are 15% below 100%. Okay, good. Let's find a... hold on, that's a decay. That's a decay. Okay, here we go. So this one, the future price of a certain item is $2,500, and over time it's going to cost more. So this one's growth because the multiply value is greater than 1, this number right here. And what percent is it changing? 5.3%. Does everybody understand that? So this is 105.3%. And so we take away 100% and we get 5.3%. All right, let's look at the next type. Okay, so we have bacteria that are increasing. So our equation is going to be y equals, hold on, got to turn on my pen. Y equals 2,800 times, we're going up or down? Up. So we take 100% and add it to 16%, and we get 116, which is 1.16 to the t. What if we were dropping? What number would I put here? 0.84. Good. 100% minus 16% is 0.84. Okay. this one's a little bit tricky, I think. Is this the one you had trouble with, Monty? Okay. To write this equation, I need y equals my starting amount. So how much is this starting out as? We have to look at the x equals 0 number. So 9 goes here. And then what are we multiplying by? How do we get from 9 to 27? Multiply by 3. Is that the same everywhere? So is it multiply by 3 from here to here? Yes. Is it multiply by 3 from here to here? Yes. So that's the equation. Now this is kind of a an interesting situation. How fast is this growing? You did it the hard way? Oh. Anyway, yeah, that's way easier. So if I multiply by 3, how fast is the population growing? It seems like 300, but it's not. Think about how we calculate growth. What do? We always subtract 100%. So if this is 300% and we subtract 100%, that means we are growing at 200%. And this is somewhere that people are really bad at knowing the difference. If you triple the population, you grow by 200%, which seems weird, right? But if we have 5 people and we triple, how many people do we end up with? 15. How much did we grow? From 5 to 15, we grew 10 people. And 10 people is what percentage of the original 5? 200%. So you have to be really careful when you talk about this. Tripling is not growing by 300%. Tripling is growing by 200%. Quadrupling is growing by 300%. And now that you know the difference, you'll hear people out there who mess this up all the time. Because they'll say, oh, we tripled, so we grew 300%. No, the first 100% already exists. So you have to subtract them off if you're going to talk about percent growth. All right, let's look at another couple of these. Okay, what's the equation here? Y equals 2 times something to the x. What are we multiplying by? 4. So, how fast are we growing? 300%. We're quadrupling, but our growth rate is 300%. Monty, were there any of these that are decay problems? I don't know that they're going to do that. What are we multiplying by here? 8. Did it have you plug in an x and a y and solve? And then it would do this. That'll work. Yeah, that does work. Oh wait, I don't call that B, I call it M. So that works, but if you can look at the table and see the multiplier, then just plug in the multiplier. But if it was like 0.37 and 0.82 and 2.4, my method's not going to work very well. Although you can just divide these. What is 0.82 divided by 0.37, and that will give you the number you want. Okay. I think this is the last one. Oh, you guys can do this. Y equals 2,000. Are we going up or down? Up. They're charging interest. How do we go up 7.5%? 1.075 to the fourth, and then just figure out what that is. What if it was dropping 7.5%? What number would I put in for M? Not good. 0.925. Oh, really? Compounded annually. Ooh. Yeah. Ooh. Do I want to do that? So, okay, so the formula is y equals p times 1 plus r over n to the nt. So, yeah, we better do this. What's happening here is no bank pays you, or no bank calculates the interest at the end of the year, because you're always moving money in and out of your bank account. So if the bank waited until the end of the year to calculate the interest, your bank account may have been really high earlier in the year. You're not going to get credit for any of that money. So what the banks have decided to do is, instead of paying 7.5% at the end of the year, we're going to give you a little bit of that percentage every day. So at the end of the day, we look at Jersey's bank account. She's got $100 in there. And the bank says, okay, you have $100. I owe you this much today. And then the next day, she has $200 in there. And the bank says, okay, now you have $200. So now I owe you interest on $200. Does that make sense? So the way that works is we need to break this into daily pieces. So how many days are in a year? So good. We'll just do 365. So we need to divide this by 365. So 7.5 divided by 365. So instead of getting 7.5% at the end of the year, you're going to get 0.02% every single day. Does that make sense? So that is called the number of compounds. So N is the number of compounds. So the original formula says, I plug in my initial amount, I'm going to get the full percentage at the end of every year. So the interest is only calculated once a year. But this formula allows us to pay interest whenever we want. And for banking, daily makes the most sense, because yesterday's balance and today's balance are probably going to be different. Okay? They could pay you interest at noon and then again at midnight, but they don't do that. Okay? So instead of getting all of your interest at the end of the year, you get a little bit of it every day. Is that better or worse? Do you want to get interest every day, or do you want to get it once at the end of the year? Every day. Why? Why is it more money? Yeah. So if we take Jersey's $200 and she gets a little bit of interest today, she's going to have more than $200 tomorrow. Does that make sense? And so she'll get interest on $200 and the little bit I paid her yesterday, so her interest is earning interest. So the more times you compound per year, the more money you're going to make. So to work this formula, we have to take the rate and divide it by how many times we pay interest. And then instead of calculating that once a year, we calculate it n times a year. So for this problem for daily, we would say y equals 2,000 times 1 plus, my interest rate is 0.07 over 365, and I'm going to raise that to the 365 times 4. Now, notice, this is not 100 plus 0.07. Hey, what's up? Okay. So let's calculate this. And watch what happens. If I do $2,500 and I times it by 1.07 to the fourth, I'm going to have $3,276. Right? That's at the end of 4 years if I only get paid once a year. But what happens if I get paid every day? So 2,500 times 1 plus my interest rate, 0.07, divided by how often I compound, 365. Raise that to 365 times 4. Now, if your calculator looks like this, anyway, you probably want to put parentheses around that. Mine I don't have to because it actually raises it to an exponent, but if you use those calculators and you get the little caret button, you need to put those in parentheses. And watch what happens. We made more money. $31 more. Okay, why is that? Because if I get paid a little bit of interest every day, that interest earns interest. So the more often you get paid, the better off you're going to be. So we need to work a couple more of these. Okay, compounded quarterly. What does that mean? 4 times a year. So the formula is y equals p times 1 plus r over n raised to the nt. So we have $4,000, and we do 1 plus 0.051 over 4, and we're going to raise that to the 4 times 7. Okay, calculator. So 4,000 times 1 plus 0.051, divided by 4. Raise that to the 4 times 7. And I get 5,703. Okay. All right. Get to work. Oh, okay. Deal.